Kinematics is the study of objects that are in motion. It's analyzing the relationships between the distance something travels, the rate at which it's traveling, the acceleration, and time. And so we've seen previously that velocity is calculated by tracking the change in distance divided by the change in time. So we can find that average velocity over some given interval. And so in more complicated circumstances, we can take these variables and apply calculus techniques to them. But for simpler circumstances, like most of what we're going to be looking at in this class, we're just going to be able to use basic algebra and geometry to relate these variables to each other. So in front of us here, we can see a distance-time diagram. So we have distance along the y-axis, we have time along the x-axis. And so we're just keeping track of the relationship between those two variables. So if we have a horizontal section to our graph, like what we see here, well, that would mean that the distance is not changing during that period of time as time is going by. So therefore the velocity would be 0. We have no rise, but we do have run. On the other hand, for this next section of the graph here, we can see that we do have a change in distance, and we have a horizontal change as well, representing some time elapsing. And so by dividing the change in the vertical and horizontal position from point A to point B, we can determine the velocity. So essentially, the velocity is going to be the slope of the line on a distance-time diagram. And so if we move forward to the next slide, we can see a diagram that's keeping track of an open water swimmer. So the distance is being kept track of in yards, and then time is being kept track in minutes. And so we're going to find the speed at which the velocity at which the swimmer is moving in feet per second. So we are going to have a little dimensional analysis that we've got to do. And so we've got 1, 2, 3, 4, 5 separate segments for which we're going to calculate those average velocities. So in segments 1, 3, and 5, there is no velocity. Because we have horizontal lines on our distance-time diagram, that indicates that there's no change in distance, as we saw in the previous example, so that means there is no velocity. So it's really only in segments 2 and 4 that we have any work that needs to be done. So if we want to find the velocity, we're going to do the change in distance. So for segment 2, our change in distance is going to be 300 yards divided by, we can see that we have a period of 2 minutes that goes by. And so if we want to convert that into feet per second, we have a little dimensional analysis work to do. And we'll gloss over our significant figures here a little bit and just assume that everything is an integer value. So we need to convert our yards to feet. So of course there's 3 feet in 1 yard. And then we need to convert our minutes into seconds. So in 1 minute, we have 60 seconds. And so if we perform those conversions and operations, we'll see that we get 7.5 feet per second. And in segment 4, we've got a change in distance of 150 yards, since we're going from 300 to 450 yards, divided by what looks to be a 4-minute interval of time. And so we'll use those same conversion factors of 3 feet to 1 yard and 1 minute to 60 seconds. And so on this one, if we calculate that out, again, glossing over our significant figures, we end up with 1.875 feet per second. So this is a distance-time diagram that relates distance, time, and velocity all in one place. A second type of kinematic diagram, and one that we'll spend more time on than the previous example, is a velocity time diagram. So this is one that's going to take those same variables of distance and velocity and time and also bring in acceleration. And so just like change in distance over change in time was velocity, So now a change in velocity over a change in time is going to give us our acceleration. So whereas the slope of the line in a distance time diagram was our velocity, the slope of a line in a velocity time diagram is going to be our acceleration. And so here, again, we have a horizontal segment where the acceleration is 0, but the object is still moving. It's just the rate at which it is traveling is not changing. So time is going by, and the object is traveling, is moving at some velocity, but there's no change in that velocity. Here in a linear section, we have a constant acceleration where we find the slope of that line to find the acceleration during that interval of time. And then if we were in a calculus-based circumstance, we could have some sort of variable acceleration where we'd have some sort of curved line representing the change in velocity. But this is not going to be the case for us. We'll leave that to Mr. Lorge and Ms. Henderson for you. So the diagram like this, as I said, is important because it connects all of the variables associated with a moving object. We've got time, we've got distance, we've got velocity, and we've got acceleration all covered. And we see it all in front of us in an intuitive manner. So the slope of the line, like I said, is going to be the acceleration of the object, and then the area underneath the curve is going to be the distance that the object has traveled during that window of time. And so it's going to be simple for us whether it's a rectangular area like the one that we see here, or if we have some sort of triangular or trapezoidal area. We're going to be working with pretty basic shapes for which we have to find the area in order to be able to find the distance. So let's move forward with a couple of examples.